Okay, so we've had a quick run through of what acids are, what it means to be an acid, how you can improve the acidity of the molecule that you're looking at. Now, acids and bases are in competition, but general chemistry really doesn't occupy itself with bases at all. And there's a good reason for that. And the reason for it is economic. Then when you get to a higher level chemistry, when you get to look at organic, it's like all we're going to talk about is the base. But in terms of bases that we see in general chemistry reactions, our big basic anion is hydroxide. And just as when you thought of the names of any acid, sulfuric acid, nitric acid, hydrochloric acid, hydrobromic acid, phosphoric acid, phosphorus acid, sulfurous acid, nitrous acid, carbonic acid, those are all formed from nonmetals, and the oxo acids, the ternary acids, are made from the oxides of nonmetals when they dissolve in water. So nonmetals are going to make acids. All of our bases are going to contain a metal. It's going to come from the other side of the periodic table, which makes complete sense. If the acids come from the right-hand side of the periodic table, then the bases should come from the left-hand side. And so we're going to see things like sodium hydroxide. Now, the deal with sodium hydroxide is very much the deal that we saw with hydrochloric acid and with hydrobromic acid and with hydroiodic acid, is that when you, so this will be a solid. Now, when you dissolve it in water, it makes NaOH, which is an aqueous solution, and that splits apart 100% into sodium ions and hydroxide ions. So if I had a 1 molar solution of sodium hydroxide, and I'm reading through my methodology for doing a particular reaction in the lab, and it said, we're going to take this many moles of hydrochloric acid and we're going to neutralize it by reacting with an equal number of moles of sodium hydroxide. It says in the method, potassium hydroxide. But you don't have any potassium hydroxide, you only have sodium hydroxide. It's going to make no difference at all, none. Because what is the sodium doing? Sodium, and we'll prove that by writing out the acid-base neutralization reactions. You will have done this in General Chemistry 1. I know that I taught it in General Chemistry 1 a couple of weeks ago. That acid plus base makes salt plus water. And then you make, remember, you make the complete ionic equation, and then you filter that down to the net ionic equation, and you find out that sodium was a spectator ion. Any of that ring a bell? Okay, well, we'll do it again. So we'll do it again really soon. This is just a spectator. It's floating around doing nothing. So, sodium hydroxide pretty much is interchangeable with potassium hydroxide. Now, hydrochloric acid is kind of interchangeable with hydrobromic acid, Problem being if you have a metal ion in solution currently whose chloride is insoluble, then you cause a precipitation. And that would be ever so slightly different, like if you had silver chloride precipitation. You did that in lab. Silver bromide also precipitates, but it's a different kind of precipitate. So pretty much interchangeable. These ones, completely interchangeable. What do we know about sodium salts? Anything at all? From solubility. Do you remember solubility rules? All sodium salts are soluble in water, all of them. So anything that you read on paper that starts sodium something, it's guaranteed to be soluble in water. What about potassium salts? Same thing, all of them, which tells us that in solution, these things are ionized, dissociated, and the potassiums and the sodiums are floating around free. They're not interacting with anything. They end up being what we call spectator ions. So this sounds like all my hydroxides are the same, which is almost true. Almost true. At which point, you buy the cheapest one. And sodium hydroxide is our best base and our cheapest. Imagine you're in the market for anything at all. Who makes the best television? Which brand of television is the best? Like Panasonic or something? I don't know. Right, so we can't give an analogy for something that I don't know about. You're in the market for a car, and it turns out that you could buy a Chevy, or you could buy a Bentley, and they both retail at exactly the same price. It should be a no-brainer at this point, right? Plus all the things that you're worried about, like service contracts or whatever. It's all included in the price. Our best one is our cheapest one, therefore we don't use any of the others. And it's as simple as that. We do have other hydroxides. If you go to group 2, we've got calcium hydroxide and magnesium hydroxide. And these end up making calcium 2 and 2 molar equivalents of hydroxide. Oh, I've switched the, like that. I think with the coefficient in front of the ion, I've switched the negative to the end. Be prepared for it to flip-flop. Okay, it's not important. Now these, as far as I can tell, these hydroxides exist so that the people who write textbooks can write other examples in the book other than sodium hydroxide. These appear to have no utility at all. These are going to be more expensive, plus, does anybody know anything at all about the solubility trends of hydroxides in group 2? It did get mentioned in General Chemistry 1, like in passing. At the top of the group, the magnesium hydroxide is not particularly soluble. This one's got a little bit of a solubility issue. As you go down the group, they get more soluble. So these ones, and I'll lump them both in, but it's definitely the magnesium, are going to be more expensive, harder to use, and of less general utility. So we don't use them. That leaves me with sodium hydroxide. which is interchangeable with potassium hydroxide if I need to. So the hydroxide has become our de facto strong base. Sodium hydroxide is pretty much, for general chemistry, the only strong base that you need to know. And then, when it comes to weak bases, the people who author general chemistry textbooks have another problem. And that problem is that now we're venturing into an area that kind of gets complicated. And so let's just pick one that is the simplest one I can think of and kind of brush over it and move on. And later on, one whole semester from now, when you get to organic chemistry, we will really define what a base is and how a base acts. And we will start every page in the textbook that we look at. Every reaction, the first thing that we're going to do is identify the base. And then we're going to see how the base interacts with its surroundings and the other reactants in the vessel. From the Arrhenius definition of a base, you won't be able to see it. From the Bronsted-Lowry definition of a base, you won't be able to see it. But from the Lewis definition of what a base is, you can predict by drawing a Lewis structure of a molecule whether it will be a base or not. What's the definition of a Lewis base?
Electron pair accepts it or doesn't.
The thing with acid is it begins with AC, and as does acceptor. So a Lewis acid is an electron pair acceptor. That means a Lewis base is an electron pair donor. Okay. If a base is an electron pair donor, what does a base have to have? A lone pair of electrons. A non-bonding pair of electrons. Where on the periodic table will we find elements that have non-bonding electrons? Non-bonding pairs of electrons. Lithium's in group 1. How many valence electrons does it have? Can it have a non-bonding pair of electrons? No, it only has one electron. Beryllium is in group 2. Can it have a non-bonding pair of electrons? No. Boron is in group 3. Can it have a pair of non-bonding electrons? Nope. Carbon has 4 unpaired electrons, makes 4 bonds. No lone pair of electrons. What about nitrogen? 1, 2, 3, 4, 5. Nitrogen is in group 5, however, it always makes 3 bonds because it has 3 unpaired electrons. Oh! And a lone pair. A pair of non-bonding electrons, which means that nitrogen atom can donate that lone pair of electrons to something else and be a base. It's not a non-metal though. So our weak bases, you're going to need a lone pair of electrons. Our weak bases have to have a lone pair of electrons. This is the one, this is the only one that the textbook is prepared to spend any time on. But if you can do it for this, then we can replace 1, 2, or all 3 of those hydrogens with carbon chains. And we have a whole family of molecules there called amines. And in reading through the text, there are a couple of questions in there of, this amine is put into solution, find out what the pH of the solution is, because it's going to be a weak base. This is ammonia. Ammonia ends in an A, not to be confused with the other word that sounds like ammonia, which is ammonium. Ium at the end of a word means what exactly? I'm going to turn my ammonia into ammonium. What does ium at the end of a word mean? The end of a name. Think of a chemical that ends in ium and blurt it out. You don't have to raise your hand. I'll get the balls rolling, shall I? Calcium. Helium. That's a really bad example, actually. That kind of breaks the rules. Go to the back of the class. Sodium. Calcium. Potassium. Keep going. It's a periodic table there. Cesium. So lithium, sodium, potassium, rubidium, cesium, francium, beryllium, magnesium, calcium, strontium, barium, radium, scandium, titanium, vanadium, chromium, ytterbium, zirconium, niobium. Molybdenum strikes me that they've spelled that wrong. Molybdenum. I think it should probably be molybdenium. I think an I slipped out of that word somewhere in its history. Oh, and then AL. What's the AL? Are you sure? Are you sure it's not aluminium? Other people in the English-speaking world call that aluminium, and it ends in IUM. IUM clearly is part of the family naming system here. What do you think IUM means? All the metals have this behavior. They all go positive. They all go positive. All the metals get oxidized. They lose their electrons and they end up making cations. Ium at the end of a word means positive. Here we go. I'm going to take my ammonia, lone pair of electrons, curved arrow, has to be curved. In chemistry, the motion of 2 electrons is described by a curved arrow. Reaches out and grabs H+. H+ is my acid. Ammonia is my base. And we go from being a trigonal pyramid to being a tetrahedron. And somewhere in there there's a positive charge. This is all these 3 are covalent bonds. If we draw the Lewis structure in, they have dots there. And then this is a coordinate covalent bond to an H+, which is just a proton, has no electrons at all. And now, can you tell me in this tetrahedral, completely symmetrical molecule, which pair of those electrons used to be the lone pair? No, it's gone. And now there's a positive in there somewhere. And sometimes we'll localize the positive on the nitrogen, because that's where it belongs. And then other times, we'll put it in square brackets and put the positive outside. These square brackets not to be confused with the ones that we use for concentration. And so sometimes people only show parts of the bracket. Just show you that. And say, I didn't bother writing the whole bracket because I didn't want to confuse you with something that could be taken a different meaning somewhere else. And so there's a positive in there somewhere. Okay? This is being a Lewis base. The Lewis base is an electron pair donor. This is being a Lewis acid. This is being an electron pair acceptor. Now we said earlier on that it was Lewis that had this epiphany of my molecules don't have to actually possess hydrogen in order to be acidic. Here's an example. I've got NH3, which is ammonia, and BF3, which is boron trifluoride. Okay, let's write out the Lewis structure. Here's the nitrogen. 1, 2, 3, 4, 5. Put the hydrogens in. Hydrogen can only make one bond. So each of those hydrogens has a covalency of 2. That nitrogen now has a valency of 8. We have satisfied the octet rule. Here's boron trifluoride. Here's the boron. Boron's in group 3. It has 3 valence electrons. And then I'm going to use each of those unpaired valence electrons to make a covalent bond to a fluorine. Here's a fluorine, and the fluorine is in group 7. And so by making one covalent bond, it satisfies its octet rule need. So here's the BF3. There you go. So I've got ammonia and BF3. Now ammonia has satisfied its octet. It's obeying the octet rule, which means you need 8 electrons in the valency. But boron has not. Those fluorines each have 8 valence electrons, but how many electrons does the boron experience right now? 6, which means it's electron deficient. And it's electron deficient by an even number of electrons. So I'm going to take that lone pair of electrons and I'm going to give it to the boron. This is the ammonia being a base. And this is the BF3 being an acid. Doesn't have any hydrogens. Doesn't affect the H plus concentration in solution. Doesn't donate any protons. But it is an acid because it accepts pairs of electrons. They have to come in pairs, just the same way that the H plus does. Yeah.
I still don't get, how do you know if it's weak or strong for the base and the acid?
These ones, hydroxides, where am I? Right here. They are going to interact directly with H plus. So an acid is anything that puts H plus into solution. If this sees H plus, it makes H2O. Okay, and just strips it out of solution. So this, because that's a direct pathway to removing H plus from solution, these are strong bases. This one, not so much. So the way that you can calculate whether something is good at being a base or not is, actually we'll get to it next, is we look at what's called the conjugate base. So in general chemistry, we're going to learn the trend for acidity. If we know the acidity trend, then we know the trend in the reverse direction also. We'll do that now. Comes down to two things that you can spot. This does not have a negative charge. If you have a negative charge, you're going to be more basic than if you don't. And your position on the periodic table determines how basic you can be. Okay. So doing now, I've got to do strengths of conjugate bases. All right. Do I do the neutralizations now or do I do it after? I'll do this now. So it said previously, you can spot an acid if it's written down because you're going to lead with the H in the chemical formula. Now, acids split apart into the H plus and the A minus. And the H plus really is the acid. All that the HA is doing is being a carrier for that acid. And the A minus is something that we call a conjugate base. A conjugate base has less H and more negative charge. And we're normally going to calculate that, count those in increments of 1, because it is possible for a conjugate base to lose more than 1 hydrogen. We usually count them up in increments of 1. So a conjugate base has less H and more negative charge than the free acid that it came from. Okay? That's my acid behavior. What a base is going to do base is going to interact with the H plus. So this is my free base. And it's going to pick up the acid. Now there's a chance that the base itself is negatively charged. If the base is negatively charged, then this is going to be called the conjugate acid. The conjugate acid doesn't have a positive, but it has one more positive than the base that it came from. This is called the conjugate acid. And the conjugate acid has more H and more positive charge. Than the free acid. Let's write a few of those down, and then I'll map them out on the periodic table and show you explicitly what the trend in acidity and the trend in basicity is. Okay? So, HCl goes to H plus and Cl minus. HCl is the free acid. H plus is the thing that actually is the acid. Arrhenius says having the H plus in solution makes the solution be acidic. That's the thing that's actually causing the solution to be acidic. And then this right here is my conjugate base. Here's an example of a strong acid. This is H2SO4. H2SO4 can lose both of those H's, but it's going to do them one at a time. And we're going to spend time looking at why the first step and the second step are not even close to being equal. But the first one is always easy, and that the second step, even for a very powerful acid like sulfuric acid, is more difficult. So we do these typically in steps of one. I didn't specifically write down that the conjugate base has one less hydrogen and one more negative charge than the free acid, to allow for the fact that there's more than one conjugate base, but it's okay to think that way. Things like nitric. So this is, I don't know how comfortable we all are with naming. You should all be good at this. This is chloride. Ide at the end of a word means negatively charged. What's this one called? SO4 minus is sulfate. 8 at the end of a word means negatively charged and contains oxygen. If the H2SO4 loses both H pluses, then you make sulfate. But it's going to do it in 2 steps. So this used to be called bisulfate because they thought that, oh, we won't call out the hydrogen, we'll just call that bi. Which is dumb, because bi means 2. Yeah, but we're using the nomenclature di to describe 2 things inside of a molecule, not bi. Well, people aren't going to know that, and they're going to think that bisulfate contains 2 sulfates. So this is hydrogen sulfate. And this is nitrate. Okay? So we're set up right here that our these are strong acids. That our conjugate base contains one less hydrogen and one more negative charge. Then we'd have things like carbonic acid. That's a weak acid. And we're going to revisit these, what we call polyprotic acids, the ones that have more than one H to donate. So we're going to revisit those and look at those steps, one after the other. So this is hydrogen carbonate, a molecule or an ion that used to be called bicarbonate. We don't call it bicarbonate anymore because, yeah, bi means contains this additional hydrogen, not that it means two of them. So you're, what would that be? A gas removal? What's the antacid? Your antacid, your bicarbonate, that's what it's for. Okay, so that's what conjugate bases look like. And there really isn't anything, because the hydroxides are going to turn into water. What we would do for the reverse is we'd say something here, like here's an ammonia, and it picks up a proton, and now this is the conjugate acid. And the conjugate acid contains one additional hydrogen and one additional positive charge. Now the other thing that we can do for conjugate acids is we can look at a weak acid and its dissociation and write it backwards. So in the case where we have salt forward reaction where the carbonic acid, here we go, we haven't named this one. Carbonic acid dissociates in equilibrium to some H plus and some hydrogen carbonate. The reverse reaction would show this picking up H plus and making the conjugate acid. This conjugate acid has one more hydrogen and one more positive charge. Well, it isn't positive itself, but it started out being negative, and a negative plus a positive ends up being uncharged. Okay, so if we can write out,
will weak acids and bases be in equilibrium most of the time?
yes, yeah. And we are eventually going to get to the point where we mix them together and we do that neutralization reaction that you all know exists. That is coming. I said earlier on, there's no specific order in which these topics have to be organized, but I'm trying to siphon eventually to some bigger point. Okay, let's look at strengths of bases. And we're going to find that by looking at the conjugate bases, okay? And we're going to find that by looking at the strengths of acids, because we've already trained our eye to spot what's going on with the acids. So I have two trends on the periodic table, left to right and top to bottom. or right to left, bottom to top. Either way, there's a horizontal trend and there's a vertical trend. And if I describe that, I've got to describe everything, right? Okay, so let's look at, here's a carbon, there's a nitrogen, here's an oxygen, here's a fluorine. Everything in group 8, the helium, the neon, the argon, the krypton, the xenon. See, there you go, helium, it's in group 2. That name doesn't belong in no, group 2, but group 8. That name doesn't belong in group 8. We should all start a petition. So what is it? Neon, argon. It should be helon. Because EM means positive charge. And it's not losing its electrons. Well, until chapter 21, when we look at nuclear chemistry, and then it does. Fluorine, chlorine, bromine, iodine, okay? Here's what I'm going to do. Those are the atoms that should sufficiently describe a vertical trend and a horizontal trend. I am going to make a family out of these atoms by doing this. I'm making the hydrides out of them. I'm taking the atom and I'm reacting them with only hydrogen. Oxygen, so F becomes HF, Cl becomes HCl, Br becomes HBr, I becomes HI. H2O becomes H2O, N becomes NH3, and C becomes CH4. Carbon's in group 4, has 4 valence electrons, unpaired, therefore always makes 4 bonds. Hydrogen's in group 1, could only make 1 bond. Okay. Here's what I know. My conjugate bases in these acid dissociation reactions are fluoride, chloride, bromide, and iodide. And because I was paying attention yesterday, I remember that hydrofluoric acid, because it's small and electronegative, doesn't dissociate 100% in solution. So that one is a weak acid. So my acidity trend goes that way. Acids are the opposite of bases. The acid is the HF, the CHCl, the HBr, and the HI. Those are the free acids. The bases are the I minus, the Br minus, the the Cl minus and the F minus. And if the acidity trend goes that way for the free acid, then the basicity for my conjugate bases goes the other way. Iodide, chloride, bromide are all things that we call, so chloride, bromide, iodide. These are strong electrolytes. When they have separated into their ions and are floating around in solution, they have no interest in recombining. None. These reactions process to the right-hand side 100%. When the Cl minus has dropped off the H plus, it has zero interest in recombining with the H plus to reform HCl. That never happens. It goes 100% that way. F minus, not the same thing at all. When it comes off, because it's so small and so electronegative, it has an interest in recombining. So this one's in equilibrium. Okay? So that acidity trend we spoke about a day or two ago, and it's mostly size, because the iodide is enormous and the fluoride is tiny. Okay, so we're going to do the same thing. If I can spot the acidity trend on the horizontal now, then I can know what the basicity trend is for the conjugate bases. Let's see if we can spot it. Anybody know what that's called? CH4? That's called methane. Ane means contains only hydrogen. So this is a hydrocarbon, contains only carbon and hydrogen. Meth means one carbon. That is methane. And this is ammonia. And that's water. And this is hydrofluoric acid. So there is a clue there in the horizontal trend of where this acidity trend is headed. Say it again, just in case you missed it. Methane, ammonia, water, hydrofluoric acid. Can you see which way the acidity trend is going? Oh, also, we wrote the H in front of the O right here. But we didn't write the H in front of the N. And we didn't write the H in front of the carbon. That's a clue. You always write the H in front of the other atom if it's an acid. So my acidity trend horizontally goes that way. All right, let's do the same thing. Let's do what we did with the verticals right there. I'm going to take this molecule and I'm going to strip it of an H plus. So its conjugate base is CH3 minus. This is something called a methyl carbanion. Carbon, anion, carbanion. My ammonia has now gone negative. Ammonia we've seen go positive and went ammonium. And when things go negative, fluoride, chloride, bromide, iodide. When they go negative, this is amide, A-M-I-D-E. Water makes hydroxide. And I don't know if I can squeeze this in. Fluoride. So I have fluoride, hydroxide, amide, carbanion. Our trend in basicity is going to go this way. So there's a little off-the-cuff remark that you can make that says the conjugate base of a strong acid is a weak base, and the conjugate base of a weak acid is a strong base. Conjugate base of a strong acid like HCl is not interested in recombining, in being a base and finding out H plus and recombining to make the acid. Conjugate base of a strong acid. Okay, so you should be able to look at the periodic table and predict, ooh, do I have a lone pair of electrons? It could be a base if I have a lone pair of electrons. Do I have a negative charge? If an atom has a lone pair of electrons, it can be a base. If it has a lone pair of electrons and a negative charge, it could really be a base. And then you look on the periodic table and you see how close to the right am I? Because as I move closer and closer to the right, I become weaker. Okay, let's do some neutralizations and see what we got. We'll start with the easy, obvious ones, and then we'll make them progress to the point where we have to look, we have to do some investigating to figure out what's really going on. We will start with the very, very straightforward middle school, high school kind of thing. Take a strong acid, and I take a strong base, and I combine them. So, HCl, so prototypical strong acid, and NaOH. Combine together to make H2O and NaCl. My HCl is in aqueous solution, my NaOH is in aqueous solution, my H2O is in L, my NaCl is in aqueous solution. acid plus base makes water plus salt. That's a generality that is going to hold true. Okay, anybody remember what classification of reaction this is? You know, we have different types of reactions. We have additions, decompositions, replacements. Remember any of those? Displacements. This is a double displacement. And in a double displacement, knowing full well that whenever we write something ionic down, we always write the cation first, the anion second. The metal first, the non-metal second. In a double displacement, you take the front of the acid and you combine it with the rear of the base to make the first object. And then you take the front of the base and the rear of the acid and you combine them. This is what we call a double displacement. Okay. So, NaOH and HCl come together to make H2O and NaCl. Yeah. If I had a 1 liter bottle filled to the brim, right up to the top, that said that this was 0.1 mole per liter hydrochloric acid, how many molecules of HCl would be inside my bottle? It's the same question as yesterday. None. None at all. Why not? Because HCl is a strong acid, which means it doesn't exist in solution. It splits apart 100%. There is no HCl in solution. There's some H's, H pluses, and there's some Cl minuses. Sodium hydroxide is a strong base. If I had a bottle, stock bottle, that said this is 250 milliliters of 0.02 molar sodium hydroxide, how much sodium hydroxide is inside the bottle? None. I got some sodiums, and I got some hydroxides. Where am I going to write the negative? I don't know. I haven't decided yet. H2O is a covalent molecule. It's a liquid. That's just water. But salt dissolved in water, all sodium salts are soluble. All potassium salts are soluble. All nitrates are soluble. Most chlorides are soluble with the exception of silver, mercury, lead, cadmium, something like that. All sodium salts are soluble. Sodium chloride is a strong electrolyte. It splits apart when you put it in solution. So this is what we call the complete ionic equation. It describes actually what's going on in solution. Break out the red pen. anything that appears on the left-hand side and the right-hand side of the equation cancels. That chloride cancels. This sodium cancels. This leaves something called the net ionic equation. Which says the thing that's generating the acid, H+, and the thing that really is the base, OH-, get together and make water. The salt is a spectator. These things that got cancelled, these are called spectator ions. They participate not at all in the reaction. They're just along for the ride. Doesn't matter. They're dissociated, 100% in solution. They're just floating around. They're not recombining with anything. They're not making anything. They're just in the way. They're not even in the way. This net ionic equation is true for all acid-base neutralizations. Okay. Could write this out again, or you could just cheat. What if I changed the acid to be nitric acid? Then I wouldn't have that chloride there anymore. I have nitrate. And what if instead of using sodium hydroxide, I used potassium hydroxide? Then I wouldn't have this sodium here anymore. I'd have potassium. I'd still make water. I'd still make a salt, but my salt would be potassium nitrate. Oh, all potassium salts are soluble in solution, so those are strong electrolytes. And all nitrates are soluble in solution, so all of those are soluble. And the nitrates cancel, and the potassiums cancel, and I end up with the same thing. Doesn't matter. Okay. Let's look what happens when we start mixing our acids and bases unevenly. If I did combination of a weak acid and a strong base. Oh, before I write that down, I'm really tempted to write something else out on the board. Let's do it. Before I get to this, because we did it in lab. Let's do this first. If I took an Erlenmeyer flask, this is the old-fashioned way of doing this experiment. We did it the modern way last week. If I took an Erlenmeyer flask and a burette, and I wanted to know how much base I had in this solution. I put the base in the Erlenmeyer. Erlenmeyer flasks are conical for a reason. That means they don't splash. You can pick them up and shake them, and they don't splash. You never ever do a titration into a beaker, which we may have done in lab, but there was no picking it up and moving it because we had a stirring station and we had a drop counter. But you normally wouldn't do that. Okay, and then I would put the acid in here. And because my potassium hydroxide is a colorless solution, and because my nitric acid is a colorless solution, I would have to add a couple of drops of an acid-base indicator. And that indicator will change color when the solution goes from being basic to acidic. Okay, and I would have to do this thing visually. So I'm doing that experiment visually. You're doing it with the pH meter and the drop counter like you did last week. So let's say this scale is pH, and this scale is volume. And it would be volume of added acid. A pH scale runs from 0 to 14, 7 being in the middle. What happens right here at the very, very beginning of time before the first drop of acid has been added? What's the pH of my solution? It's a base. It's a strong base. It's a solution of a strong base. It could have a pH of 12. It could have a pH of 13. It's going to be a big number. And then as I add acid over time, that pH kind of drains off a little bit and then makes this sharp sigmoidal curve. And what we do when you're doing that by hand is you draw this out. And you draw that out, and then you find the line that is 90 degrees to both of those, and it crosses, that's my equivalence point. This is acidic. It will have a pH that is a low number. This is basic. It will have a pH that is a high number. This is pure water. It should have a pH of 7. It's neutral. And then the sodium chloride and the potassium nitrate should not be entering into this conversation at all. These are strong electrolytes. They just float around and do nothing. So that should stay neutral as well. And there's my equivalence point. We did it the opposite way in lab. We added base to acid, and we see the curve go the other way. Started at a low number and went up. Okay. There is something else on this graph that we can plot. So halfway down the steep part is the equivalence. And then as this curves out like this, halfway along this, if we plot that back, it's going to reveal a mysterious number that we haven't introduced yet, called pKa. But we know what Ka is, and we also know what P is. What is P? It's the same P as in pH. Negative of the log to the base 10 of Ka turns out to be our pKa, and this is going to be a number. It's a low number, and that will reveal what the pKa of our acid is. Okay. get through 2 examples, and then we'll take a break. Those things that I just drew on the board, that's called a titration curve, if you wanted to label that yourself. So what did I say, weak acid? And strong base. We did one of those in lab as well. We used ethanoic acid, which is also called acetic acid, but we could just invent one. Where did they go? I actually got acetic acid. There's no real nice way of doing this. We really should write the sodiums first. We're going to end up doing it the organic way and having the sodium be at the back to show that it's the H that is replaced. So this is acetic acid, or should be called ethanoic acid. And then this, my salt here, is called sodium acetate. The deal being that acetic acid does not dissociate 100%. Does not. Which means weak acid, its conjugate base of a weak acid is strong. And what do bases do? Bases take the H plus and they pull it back out of solution, which is basically just going back that way. So what we end up with, if we did our titration the way that we had done previously, and we added base to, there's 14, here's 7, and here's 0, what we would see this. This curve now is a lot further away from the baseline than it was before. When we did it in lab, we started at a pH of about 4. It was in the 4s even. And it went up, and then strong base is going to get close to 14. Okay. So when we look at where our equivalence point is now, the equivalence point is above pH 7. So you take equal numbers of moles of these molecules and you mix them together and they annihilate one another, but your solution stays basic. So equivalence is equal numbers of moles of acid and base have reacted. And there's 2 ways of looking at that. There's just the simplistic way of this is a weak acid and that's a strong base, and therefore strong base is going to win and my solution should be basic. That's too simplistic. That's not actually how it happens. What happens is the base, the conjugate base that you've created in doing this neutralization, like, adds to the total base that's in solution. And that base strips the H plus out of solution, pushes it back. And so this is, you know, where you should have been if it was a strong acid and a strong base. And then here's my additional effort from this base right here, pushing my value up. One more. Strong acid and weak base. And the other thing, so we've got our equivalence point that is halfway down that curve. If we look at halfway down this curve, and we read off, we'd find out the pKa right here. And the pKa for our weak acid is going to be a bigger number than the pKa of something that's a stronger acid. Okay, let's take HCl and react it. We really only have one textbook example of a weak base, and that is ammonia. In order to make acid plus base, make salt plus water work, instead of calling this an H plus, you need to make it an H3O plus. There's your salt. Okay. If you make this H3O plus Cl minus, you also get the water. We would see this is volume of added acid. Okay, we started with the weak base. Initial pH is not going to be so high. Weak base is not going to be able to strip so much H plus out of solution to give me a strong number for a pH. Does the same thing, makes the curve look like this. So now the curve is gapped at the top, but close to the baseline at the bottom. Halfway down that curve, here's my equivalence point. Now my equivalence point is less than pH 7. Okay. All right, let's take a break and we'll come back and we'll do some math. A bit of math. We're going to do some Kas and some pKas.